Hey, welcome back everyone, it's Kevin. Last time we talked about basic binary numbering, and that's going to help us out in this video as we take a look at basic subnetting. When we talk about subnetting, what we're talking about is taking an IP version 4 in this video, an IP version 4 address, and drawing a line down the middle of those 32 bits somewhere. And some of those 32 bits are going to represent the network address, and the rest of those bits are going to represent the host address. Now, let me illustrate this with a metaphor. We know that we're going to be dealing with a 32-bit string of binary numbers. Think of that string as a metaphor as being like this string. Here I've got a string, and what a subnet mask is going to do, a subnet mask is going to cut that string in two. So now we have a portion of that string that are host bits and a portion that are network bits. And what I want to do right now, let me tie this together. Put a big knot in this string. So here's what we have. We've got our 32-bit string, and there's this dividing point in the middle, and we're going to say that maybe these bits are network bits and these bits are host bits. And what we're going to learn in this video is this dividing point where I just cut the string, we can move it. There's a default place for it, but we can move it. Let's say we want more network bits, no problem. We simply move that dividing line. So now we've got a lot more network bits and fewer host bits. If we need more hosts, we can go in the other direction. We can have more host bits and fewer network bits. It just depends on our design goals. We're going to give you some examples where we say, you need this many hosts or you need this many subnets. What sort of subnet mask should you come up with to accommodate those needs? Let's go into the slides now and take a look at basic subnetting.
In our previous video, we took a look at binary numbering. And in this video, we're going to leverage what we learned in that previous video to do some basic subnetting. And by basic subnetting, we're answering design questions such as, what subnet mask should we use to accommodate a certain number of hosts or a certain number of subnets? Next time, we'll take a look at advanced subnetting, and this is where we ask a question such as, now that we've determined that we're going to create these 6 subnets, what are they? What are the actual address ranges in those different subnets? That's next time. And finally, we will wrap up our discussion of IP addressing by taking a look at IP version 6, because what we're talking about right now is the most widely deployed IP version 4. Now, let's get into IP version 4 basic subnetting right now by reviewing the structure of an IP version 4 address. It's a 32-bit address, and we see on screen that we have 32 binary bits. I won't read them all out, but if you count them, there are 32 binary bits on screen. And the way we write this is typically not as 32 individual bits. That would be very time-consuming and error-prone. What we're going to do instead is we're going to use dotted decimal notation. We're going to say that this IP address is 10.1.2.3. You see, it's dotted decimal notation, and what the dots are separating are octets. An octet is a collection of 8 bits. We could think of it as a byte. That's really what it is. We have these 4 8-bit components that make up our 32-bit IP address. That's going to make it a lot easier for us to write. But of those 32 bits, a portion of those bits represent the network address, and a portion represent the host on that network. How do we know which of these 32 bits are network bits and which are host bits? We need more information. We need to know what the subnet mask is. The subnet mask tells us where that dividing line lives. And we'll see why in just a few moments that we have an 8-bit subnet mask here. Notice that we're saying that the first octet is made up of network bits, and the remaining octets are made up of host bits. And the way we write our subnet mask, again, we're not going to be writing out all 32 bits typically. We're going to either say that we have a subnet mask of /8, a /8, that's called slash notation, or some people call it CIDR notation, CIDR. Or another way of writing it is to say we have a subnet mask of 255.0.0.0. Remember from our last video where we talked about binary to decimal conversion? If you take 8 ones in binary and convert that into decimal, you get 255. So this is 255.0.0.0, or we could say /8. That's our subnet mask. That tells us where we draw this dividing line, saying what's the network portion, what's the host portion. And now that we know where the dividing line lives, we're able to answer the question, what network is this IP address residing on? Later, when we get into advanced subnetting, we'll want to make sure that all of the hosts on a common subnet have IP addresses on that same subnet, so they can talk to one another and they can get off of their subnet. And based on what we now know, we could say that the network address is 10.0.0.0. You see what we did? We took the subnet mask and we said, wherever there is a 1 in the subnet mask, the corresponding bit position in the IP address is part of the network address. When we have a 0 in the subnet mask, the corresponding bit position in the IP address, that's the host portion of the address. That's going to be set to 0 when we're writing out the network address. In fact, the network address, some people call it the address of the wire, that's where all host bits are set to 0. You might want to put that one in your notes. That's critical to know. A network address has all of its host bits set to 0. And that's exactly what we've done here. We've set all of our host bits to 0, giving us a network address of 10.0.0.0. And you might be wondering, how did we know that the subnet mask consisted of 8 bits? Why did it not have 16 or 24 bits or some other number of bits? Well, it could have. What we were using was the default subnet mask, sometimes called the classful subnet mask. Here's what I mean by that. We have different classes of IP addresses, class A, B, C, D, and E. When it comes to addressing our hosts, they're only going to have a class A, a class B, or a class C address. A class D address, that's used for something called multicasting. We can send to a class D address, that's a multicast group address, but there's no host that will ever be assigned a class D address. Class D addresses are destination-only addresses. And class E, you see in the literature it says that it's used for experimental purposes. Well, I've been in networking for over 2 decades now. I've never seen an experimenter. I've never seen anything using a Class E address. They're just sort of there, but you'll probably not be using them. And you can see also on screen how we know that an IP address is a Class A or B or C. It entirely depends on the first octet. If the first octet is in the range of 1 through 126, it's Class A. If the first octet is in the range of 128 through 191, it's Class B. If the first octet has a value in the range of 192 through 223, it's Class C. And we see the default or the classful subnet masks that are assigned to classes A, B, and C. We have 255.0.0.0 for Class A, 255.255.0.0. We're splitting it down the middle for Class B, and 255.255.255.0 for Class C. Those are the defaults. And you see the slash notation as well, also called CIDR notation, or here we're calling it prefix notation. Any of those terms are valid. A couple of things I need you to understand. Number one, we don't have to use the default subnet mask. If we need additional subnets, and we can live with fewer hosts per subnet, we can do that. If somebody gives us a Class C network of 192.168.1.0/24, the default, and we're told to carve that up into additional subnets, we could do that simply by adding bits to the network portion and taking bits away from the host portion. In fact, here are the potential values that we could have for a subnet mask. We don't always end our subnet masks nice and neat at the octet boundaries. No, we could have as few as 8 bits in our subnet mask, or as many as 30. In fact, I guess we could have 32 as well. That would be a specific IP address. And on screen you see that I've indicated the classful subnet masks for classes A, B, and C, but we don't have to have one of those classful masks. We could be using something else. But here's the second big point, and this is so often confused. Please make sure you get this. Even if I extend my network bits, in other words, I'm not using the default subnet mask, that has nothing to do with the class of address I have. Here's what I mean. If I took the network of 172.16.1.0, 172 That's a Class B network. That has a default subnet mask of 255.255.0.0. If I took that network and I gave it a subnet mask of 255.255.255.0, I gave it a 24-bit subnet mask. If I do that, it's still a Class B network. Yes, I've given it the subnet mask, that's the subnet mask of Class C, but that has nothing to do with the class of address. The class of address is entirely dependent on the first octet. It does not matter what your subnet mask is. It doesn't matter if I say you've got a 27-bit subnet mask. If the first octet is a 10, it's still Class A. That's a big point of confusion. That's why I emphasize it so much. And another reason we needed to go through the binary review that we did in the last video is we need to know within an octet, if I see a 240 in the octet or I see a 224 in the octet, I need to know just off the top of my head, how many contiguous ones do I have that make up a number of 224 or 240? Here's a table I'd like you to memorize, or at least be able to calculate and write out on some scratch paper. If you see in an octet that we have a value of 240, maybe our subnet mask is 255.255.240.0, you know in the first octet we have 8 ones because 8 ones make 255. Same thing for the second octet. But in the third octet we said we had a 240. That means we have 4 contiguous ones. And whatever's left are going to be zeros, obviously. So that means that in that third octet, we have 1, 1, 1, 1, 0, 0, 0, 0. It's important to know these values and the number of ones that they represent. Let's go through a couple of exercises to reinforce these concepts. In our first practice exercise on subnet notation, we're given a subnet mask of 255.255.255.248. My question to you is this. What is the corresponding prefix notation? In other words, it's going to be slash something would be another way of writing 255.255.255.248. What is it? You might want to pause the video right now and do the calculation and come back and we'll go through the answer together. Well, let's take a look at our answer. We had a subnet mask of 255.255.255.248. And given that subnet mask, we should know that the first 3 octets are packed full of ones because they're 255. That means we have 24 contiguous ones, 8 plus 8 plus 8. So we've at least got 24 ones, and then we zoom in on that 4th octet, the final octet, and we're asking how many additional ones would I have to come up with a 248? That goes back to the table that I said you should memorize. And it requires 5 ones to give us a value of 248. So that means if we add everything together, we've got our 24 ones from the first 3 octets, and we've got the 5 ones from the 4th octet. That's going to give us a grand total of 29 contiguous ones. By the way, how many host bits are we going to have? 3. Remember, we're totaling up to 32 bits, and I just told you that we had 29 of these bits being used for the network address. That means we're going to have 3 bits left for the host portion of the address. But that's not the question at hand right now. Right now we're saying what's the prefix notation? Since we've determined that we have 29 contiguous bits, the prefix notation, or the slash notation, or the cider notation if you prefer, is /29. Let's do another one. In this question we're saying we're given the slash notation, or the prefix notation, and it's a subnet mask of /17. Let's go in the other direction and calculate the corresponding dotted decimal notation. What is going to be the subnet mask in dotted decimal? Again, you might want to pause the video and come back after you've done your calculation. Let's take a look at the answer. We had a subnet mask that could be written as /17. We know that we have 8 bits per octet, so that tells us immediately that the first 2 octets are full of ones. That means we're starting out with 255.255, and that's going to represent 16 of our 17 ones. That means we're going to have 1 1 in the 3rd octet. And if we have a single 1 in that 3rd octet following these first 2 octets that are 255, what is that? Well, we know from our binary conversion skills that a 1 followed by 7 zeros, that's a 128. That means that that 3rd octet has a decimal value of 128. All the remaining bits are going to be zeros in the subnet mask. All the right justified bits, by definition, are going to be zeros. This is going to give us a subnet mask in dotted decimal notation of 255.255.128. because our third octet is 1 followed by 7 zeros, dot 0. Now let's get into some design. Let's say that we need to support a certain number of assignable IP addresses in a subnet, and our task is to determine what the subnet mask should be. How many bits should we have in the subnet mask? Here's the formula. The formula is 2 raised to the power of h, and from that we're going to subtract 2. And h, that's the number of host bits. For example, let's take just a classful subnet mask of 255.255.255.0. That's the default class C subnet mask. How many host bits do we have? 8. We have 8 host bits. What is 2 raised to the power of 8? It's 256. What's 256 minus 2? It's 254. 254, that's the number of assignable IP addresses that we would have in that octet. And you might wonder, why are we subtracting 2? Why don't I get to use all 256? Well, let's think about this for a second. In that fourth octet in my example, if everything is set to a 0, if all the host bits are set to a 0, isn't that what we said is the address of the network? The address of the wire? So we're not able to assign the network address to a host. It's already used. That's the network address. Similarly, we cannot have host bits that are all 1s assigned to a host. Because if we had, let's say, 192.168.1.255/24, in other words, all the host bits are set to 1s, you know what that is? That's something called a directed broadcast. A directed broadcast is destined for all of the hosts in a network. In my example, 192.168.1.255/24, that means I would be addressing all of the hosts in the 192.168.1.0/24 subnet. So we cannot have host bits that are all 1s, and we cannot have host bits that are all 0s assigned to a host. That's the reason we're subtracting 2. We could attack this from a different angle. We could say, I need to support a certain number of subnets. How do I know how many bits I need to have in my subnet mask to create a certain number of subnets? Well, here we're using a different formula. It's 2 raised to the power of s, where s is the number of borrowed bits. We haven't yet talked about borrowed bits. Remember we said that we could extend the default subnet mask? We could add 1s on to the default subnet mask? The ones that we add on are called borrowed bits. Let's say that I had a network address of 172.16.20.0/27. How many borrowed bits would I have? Well, remember, we look at the first octet to determine the address class. If it begins with 172, it's a class B address. We need to memorize those ranges. And a class B network has a default, a classful, a natural subnet mask of 16 bits. And here I'm saying we're using a 27-bit mask. How many bits beyond the natural mask, as it's sometimes called, are we using? 11. We're using 11 extra bits in the subnet mask. In other words, we have 11 borrowed bits. How many subnets does that create? Well, it's 2 raised to the power of 11. And we can do that math to see what that would be. 2 raised to the power of 11 gives us 2,048 subnets that would be created if we used a 27-bit subnet mask with the Class B network. Let's now reinforce all of this with a couple of examples. In our first example, we're being told that your company has been assigned the 172.20.0.0/16 network. That's a Class B network with a default subnet mask. We've been assigned that network for use at one of our sites. We need to use a subnet mask that will accommodate 47 subnets, and we want to do that while maximizing the number of hosts we can have per subnet. What mask will we use? We'll go through the answer together, but if you want to challenge yourself right now, you might want to pause the video and then come back in a few moments and check out the answer. Well, how did you do? Did you do this on your own? Let's see if we agree on our answers. The first thing we do is we might want to write out on some scratch paper the different powers of 2. Remember the formula? It was 2 raised to the power of s, where s was the number of borrowed bits. If we wrote that out, we might get a table that looks a lot like this. We see that with 5 borrowed bits, 2 raised to the 5th power is 32. That would give us 32 subnets. 2 raised to the 6th power is 64. We're looking for a subnet mask that will accommodate 47 subnets, and 47 is not a number we come up with here, but we're not able to go with 5 borrowed bits because that's not quite enough. We need to round up. We need to round up to 6. We could use 6 subnet bits, and that would give us 47 subnets. And a few subnets beyond that even. But we have to round up because 5 is simply not enough. You might say that we could use 7 or 8 or 9. Those would all give us 47 subnets and a lot more. But remember how the task was phrased? We were told that we wanted to accommodate 47 subnets while simultaneously maximizing the number of hosts. And if we just kept making the subnet mask longer and longer, we're decreasing the number of supported hosts. So the sweet spot here is 6 borrowed bits. That's just enough and no more. And if we use 6 borrowed bits, what kind of subnet mask is that going to give us? Well, we want to support 47 subnets, and we said that 5 borrowed bits were not enough, so we're going to go with 6 borrowed bits because that's more than enough. We're going to use 6 borrowed bits and add that to the default subnet mask of 16 bits. 6 plus 16, that's going to give us a 22-bit subnet mask. And we can write that 22-bit subnet mask in a couple of different ways. If we wrote it as a dotted decimal, that would be 255.255.252.0, or if we wrote it with the slash notation, the prefix notation, that would simply be a /22. Let's do one more. Here we're being told that your company has been assigned the 172.20.0.0/16 network for use at one of its sites. And we need to calculate a subnet mask that will accommodate 100 hosts per subnet while maximizing the number of available subnets. What subnet mask will we use? This goes back to our formula where we were going to take 2 and raise it to the power of h, where h was the number of host bits, and from that we were going to subtract 2, because the host bits could not be all zeros and they could not be all ones. You might want to pause the video once again and do the calculation on your own, and then come back and see if we agree on our answers. Let's check out the result of this exercise. We're told that we wanted to accommodate 100 hosts per subnet while maximizing the number of available subnets. Another way of saying that is we don't want to use more host bits than we need. We want to have enough to support 100 hosts, but no more. To calculate that, we might write out a table like this. This is using that formula 2 to the h minus 2. If we had 6 host bits, that would give us 64 minus 2. 2 to the 6th is 64, minus 2 is 62. That's not enough, is it? Because we need to support 100 hosts. What if we used 7 host bits? 2 to the 7th is 128. 128 minus 2 is 126. So 7 host bits would give us 126 supported hosts. That's the number we need to go with. We need to have 7 host bits. That's really all we need to know to calculate our answer. We know that we're trying to calculate a subnet mask that's going to support 100 hosts. We now know that it's going to take 7 host bits to support those 100 hosts because 6 host bits are not enough. Since they're not enough, we need to round up and use 7. And if we use 7 host bits, and we know that there are 32 bits total in our address, what is 32 minus 7? It's 25. So by doing some basic subtraction, we can determine that we're going to use a 25-bit subnet mask. What does a 25-bit subnet mask look like? We could write it as /25, but if we wanted to do that in dotted decimal notation, we could write it out as 255.255.255.128. To sum up what we've talked about in this video, we said that in a 32-bit IP address, some of the bits are host bits, some of the bits are network bits. The network bits are left justified, the host bits are right justified. The subnet mask tells us where we draw the line in the middle of those bits to say what's the network portion, what's the host portion. We saw the default subnet masks for classes A, B, and C. We said that we could adjust those defaults. We could extend the number of bits in a subnet mask to accommodate additional subnets. And we gave you a couple of very important formulas. The formula to say how many borrowed bits do we need to accommodate a certain number of subnets, and another formula was how many host bits do I need to accommodate a certain number of hosts, and we went through a grand total of 4 different exercises. I hope you enjoyed this discussion on basic subnetting, but join us back for the next video on advanced subnetting, where we're going to ask the question, now that we've carved out these, let's say, 8 subnets, what are those 8 subnets? What are the IP address ranges of these subnets that we've created? We'll talk about that next time.